What you are looking at here is the wave-like nature of light. Here is a wave interference pattern produced by passing light through double slits, similar to how a water wave would interfere or a sound wave would interfere. Light also exhibits these properties. Thomas Young demonstrated using a similar experiment, although without this technology, that light indeed behaved like a wave, which gave us a lot of information about light and how it behaves. So what I am doing here is I am passing a red laser through a double slit arrangement, which is causing the waves to separate and then interfere constructively and destructively. The destructive interference is the dark bands. That's where the waves are meeting and canceling with each other. The bright spots you see are where the waves are adding together and producing a higher intensity. This is characteristic of wave interference, and we can actually determine exactly where these spots will land based on the measurements from this optical bench, but we're not going to get into that. All I wanted to do with this was demonstrate the wave-like nature of light.
Now that we know light is a wave, we are going to just talk about some of the basic properties of a wave, specifically wavelength and frequency. Now, a wavelength is when the cycle repeats itself. So what I have here is actually a cycle and a half. So I've drawn this so some people like the crest to crest. I actually like it from here to here to describe a wavelength, but it's the same. It's when the cycle repeats itself. So if it starts here, goes all the way down, comes all the way back up, then it's repeated itself and it's making a repeated pattern, and that's what we call a cycle. So that's one cycle or one wavelength of a wave. Okay, so now waves will travel. If I do this along a rope, it will travel on to the other end of the rope and possibly back, depending on how it's reflected. But waves, as they travel, then are going to have a characteristic frequency. So if this wave is traveling at some speed v, marker's dying a little bit, sometime later, we'll take this as time 1 in the black wave here, and if we say sometime later, this wave has traveled, and now it looks something like this. Frequency is the amount of times a crest passes a given point per unit time. Okay, so if I have this given point, this crest moved this much, and that was one cycle. So we call that frequency, and that's cycles per second, because it's moving along. How many times it passes, how many times a crest passes this point is the way we'll define frequency. And for that, we use this funky looking v, which is mu, not v. That was our velocity. Turns out with light, we call it c. But that is your frequency. So when we talk about frequency and wavelength, that is what we were talking about when it comes to light. Now, when we think of light, we think about the actual light we can see. We turn on a light and we call that light. Well, we only see a very, very, very narrow band of the spectrum. Light actually has a whole range of wavelengths, going all the way down to longer waves like radio waves and infrared rays, all the way to UV rays and really high energetic rays like X-rays and gamma rays. So when we refer to light, we also call it radiation, but it's all the same. There's just many wavelengths we can't see. Our cell phones operate on radio waves, our microwaves operate on microwaves. These are all the same phenomenon. They're all a property of light. And we just see a very narrow band of that light. So when we refer to light, we talk about the whole range of frequencies and wavelengths. Why is the sky blue? Why are sunsets red? This is something that kind of covered a little bit weakly in your textbook, but I just wanted to point out that it deals with, and I'm turning it the wrong way, it deals with that scattering is proportional to 1 over the wavelength to the 4th. So we just talked about wavelengths, and what we know is that the wavelength of blue light is much shorter than red light. So if you have a really small number here, this is 1 over a really small number, which ends up making the intensity I. Sorry, I didn't define that. This is the intensity, this is the wavelength. The intensity explodes when you have of what you see when you have a shorter wavelength. When you have a longer wavelength, then this number gets really small and the intensity gets really small. So this is a property of scattering by the atmosphere. So the result of that is I have drawn these two different scenarios. Here's the daytime scenario, here's the sunlight, and this is like the atmosphere thickness, okay? So if I want to trace what the blue light does, it comes in and it bounces in all sorts of different directions, okay? And I can scatter it all sorts of different ways, and it ends up reaching me, and some of it goes out to space, blah, blah, blah. Okay, so I end up seeing it coming from all different directions. I end up seeing the blue light come from all different directions. The red light isn't scattered as well, so it only comes mostly straight through. So I don't see as much red light as I do because I am not seeing the red light from over here. I'm not seeing the red light from over here. I'm only seeing the red light that's coming straight through. The blue light, though, I see coming from every single direction that there is. So I end up seeing a blue sky. A lot of people would think it's like the reflection of the water on Earth, but in reality, it has to do with scattering and the intensity of the light being proportional to 1 over the wavelength to the 4th. Now let's look at the case of the sunset here. So you see a red sunset, and you wonder, well, why is it red? I mean, the sun was up all day, the sun looked white in the sky, now everything looks red. Well, what happens is now the scattering can go in all sorts of directions because I got much more thick atmosphere here. So it's doing the same thing, same kind of property. It's kicking meandering paths, bouncing off of the molecules in the atmosphere. And some actually reach me, while a lot of the others go in the other directions, okay? So some of the blue light reaches me, but the red light, it can just pass through, and I end up seeing mostly red light because the atmosphere was a bigger chunk of atmosphere than in this case. When it's directly overhead, it's less atmosphere. When it's at an angle like this, it's going a lot further through the light's traveling a lot further through the atmosphere. So most of that blue light essentially gets filtered out. So you don't see such blue light. You see some blue, but you end up seeing mostly red at a sunset, and this has to do with light scattering. So now you know why the sky is blue, why sunsets are red. When you heat an object, that thermal energy is converted into light energy, and the density of an object can determine what wavelengths are emitted by that object. So if you heat a really dense object, it will emit wavelengths of all properties because we've got all sorts of atoms, and we'll talk about that a little bit with spectroscopy. If you heat a diffuse object, it's only going to do discrete wavelengths. It's only going to emit discrete wavelengths. So basically what I have drawn here is a light bulb, and it's got a filament. This is usually made out of like tungsten or something, and it's really dense. It's really densely packed. So you heat it up, and it emits, and I drew just the 3 primary colors, it emits wavelengths of all colors. So you end up getting the whole spectrum of visible light coming from an incandescent bulb because this filament is really dense. On the other hand, say a diffuse gas like neon in a tube, if you heat that up or excite it with electricity, it ends up just emitting red light, and we'll talk about that with spectroscopy, why it ends up being red. The point of the matter is that the dense objects will emit light of all wavelengths, whereas diffuse objects are only giving discrete wavelengths. And what this will do is lead us into blackbody radiation. So I'll get into the spectroscopy of this in a little bit, but let's talk about blackbody radiation first, which is a nice way to measure the temperature of a star based on intensity versus wavelength plots. We've been talking about wavelength now a little bit. So a perfect blackbody is an object, a dense object, that doesn't reflect light. It absorbs all the light that falls onto it. That's a perfect blackbody. Perfect blackbodies don't really exist, but an idealized case is it absorbs all the light that is onto it. So then when you heat it up, you can determine stuff from its spectra from the blackbody radiation that is emitted off of the object. So contrary to your perception of calling something a blackbody in which you see no light coming off of it, the sun is a very, very dense object, so we consider that a blackbody. And what that does is it allows us to determine the temperatures of stars, although there's a more accurate way using spectroscopy, but it's important to learn a general rule of determining the temperature of stars using blackbody curves. So what an astronomer will do would be to gather the light from gather the light from his or her telescope, and then record the intensity and plot it versus the wavelengths. Okay, so if I have the intensity, which is the amount of that light that is absorbed, say like on a CCD plate or something like that, so this is going to be intensity. It would be like watts per unit per area squared, something like that. And then this is wavelength of the light that is gathered. All right, so if you plot, let's say you have some blue light over here, and this ends up being your peak value, and that ends up being the most intense. You get the most out of blue light that you gather, it ends up being this wavelength of blue. Okay, so somewhere over here you've got red, it's not as intense. You've got green somewhere over here, it's not as intense. But there's also the ultraviolet spectrum over here. There's also the radio spectrum over here. So, on the infrared spectrum over here. So, even though you only see a band of it, we can determine an object's temperature based on that, but that whole band does exist there. So really the whole curve, if I was to trace this whole curve, would go something like this and outward. So this is the peak wavelength. This is what we call the lambda max because it's the most intense. Intensity is more the more I get up this way. I've got green line here, I've got wavelength and increasing wavelength going this way. So I've got the UV down here, which I'll actually write in. I got UV down here, and I've got red all the way down over here. So this is the infrared spectrum because as wavelength increases, UV is smaller than the red, and red is longer, so that's over here. So if you take the spectrum of the star and you plot or if you take the light from a star and you plot the intensity you gather versus the wavelength, you end up with curves like this. Well, it turns out that you can use Wien's law, I don't know how it's said, you can use Wien's law to get a pretty good estimate as to what the temperature of the star is. So this is a very odd number. He determined this experimentally over temperature. So this is a constant, and this is the temperature, and this is the lambda max, where this is the lambda max. So in this case, it was blue light. So you can actually determine a star's temperature based on that schematic. Because if I just do a little algebra here, it's like, I know you don't want to do algebra, but I can just say I have this peak wavelength. This is Kelvin meters, by the way, that's what that unit is. Kelvin is the absolute temperature scale. It's more accurate than using Celsius or Fahrenheit, but we're not going to get into that too much. So if I know the peak lambda max, I can determine the object's temperature of the star. Okay. So let's say I measure another star, like say this is Rigel, which I believe is blue in Betelgeuse. Rigel in Orion. I believe is a blue star. And well, let's say I look at Betelgeuse, which is a red star, and I get this plot, which doesn't quite go up as sharply. And my peak wavelength ends up being there. So this is for a blue star here. Oh. This is for a lambda max for a red star. And this is the lambda max for a blue star. And I don't really do that fluidly. Why not just keep consistent here. And we'll say lambda max. Okay, so for a blue star, you end up getting a light curve that looks like this. A red star, you get a body curve, or a black body curve that looks like this. Black body curve with the peak being at blue, black body curve with the peak being at red, so you see mostly the red light coming from the star. And as it turns out, if you actually calculate this, again, as we were talking about with scattering before, the lambda max for blue light is going to be, the wavelength's a lot smaller. That means this number is going to be a lot bigger. Okay, so the hotter the temperature, the smaller the wavelength, the hotter the star is. So if I get so that when you see a blue star in the sky and it's very blue relative to the other stars, that means it's really hot. This is akin to if I take a flame, like say I start a campfire or something, And at first, all I see is glowing orange and red, and only when those flames are really going do I start seeing blue off the top of those flames. Well, that's because that's the hottest. It's a comparison. It's not exactly the same how that works at all, but I'm just kind of making a comparison so you can remember it, like a mnemonic device, right? And so if it's not quite as hot, like the coal's just sitting there, you see red, but you don't see any blue. Now this is just an analogy. It works totally different with campfires. It's just an analogy and a mnemonic device to remember. Blue stars are really hot, red stars are cooler, and it has to do with Wien's law and this plot of wavelength versus intensity. So there's going to be some nice exercises that we'll do in the lab, in which you can see three different curves. One in which there's a yellow, which is in this band here at the peak. But the important thing to remember is a red star, like Betelgeuse, is not as hot as a blue star, like Rigel. These are both in the constellation Orion, which is everybody's favorite constellation. So this is how you use a blackbody curve to determine the temperature of the star you're studying, and it's inversely proportional to the wavelength. So the smaller the wavelength, the hotter the temperature. The longer the wavelength, the cooler the temperature. The study of astronomy is essentially the study of light, because we can't travel to these locations and actually physically collect data, although now we have probes that can on some of the planets. But pretty much throughout millennia, all we've been using is light to study astronomy, except for the occasional meteorite that might hit Earth. So one of the most important tools that we can use with light is spectroscopy. Spectroscopy, we can determine the composition of stars, we can determine the temperatures of stars, we can also determine the motion of stars relative to us, whether they're moving towards us or away from us. And we can even determine the rotational rates of stars, which in turn actually can lead to determining their ages as well. So what we want to get into first is basically what happens when light interacts with matter. So here's a basic schematic of an atom. I don't want to really talk too much about these orbits because they act differently than we think of. What they actually are energy levels. So the electron's somewhere out here. It wants to be close to this guy because the electron is negatively charged, the nucleus is positively charged, opposites attract. It wants to be here. So in order to get it up to here, we have to give it energy somehow. So this is basically what happens when light comes in and it enters the atom. It'll bump up the electron. So let's say I have a blue light wave, which I'm not calling this hydrogen, so not yet, but let's just say we have a blue light wave, and it bumps up the electron to this higher energy level. So now the electron's up here, and it doesn't want to be up there. So after a few seconds, milliseconds at that, or nanoseconds even, it jumps right back down and re-emits that blue light. All the other light that comes through will pass through if it's not at a specific energy, frequency, or wavelength. So when we're referring to photons, we're talking about energy, frequency, and wavelength. A photon we can picture as a little corpuscle, but in general, it's not necessarily the correct way to picture what light actually is. But it's like a particle-wave duality because it's got both particle and wave properties. So it'll come in with a specific energy, and the properties of atoms, and these electrons are only allowed in certain locations. They can't be in between these energy levels. They have to be at one or the other. They can't be in there at all, which is a weird counterintuitive property of atoms that we're not necessarily accustomed to thinking of, which is why I don't necessarily want to call them orbits, because they're not necessarily orbiting either, but they tend to be closer to the nucleus at lower energy levels. So what I need to do then is, or what this will happen here is that it'll only allow, for specific elements, will only allow the absorption of specific energies because it has to equal exactly the difference between these energy levels. So it'll absorb this light, and it'll stay up here in this unstable position for a little bit, and then it'll jump back down, and as it goes down, it will re-emit that light. Okay? Now it can jump up. It can absorb a wavelength with an energy that corresponds to lifting it all the way up to here, and then that'll be a completely different wavelength, and it can jump all the way back down, emitting that same amount of energy, or it can split that and go down to one here, emit one wavelength. This gets a little confusing, and then when you go jump from this level down to here, it'll re-emit that wavelength equal to that because that was the difference of energy levels. So that's a basic schematic of how that happens. It allows all other energies, all other wavelengths to pass through except for one specifically defined by that particular element. Each element, each atom will only absorb and re-emit certain energies, and it allows all the other wavelengths and energies to pass through. So what it ends up doing is that you can take a prism, separate the light into the different wavelengths. So what a prism does is you have, say, a prism. The best way to draw it's probably like that. And you have light waves coming in, which in general you'd have to say that light is white because it comes in white from incandescent bulbs. So let's just assume this is a light wave. Let's say, right, and then it passes through, and I can't remember which is on top. It separates it into various colors. So it'll separate it into various colors, and that's what happens with a prism. And this happens to deal with how light travels through. Light travels through different materials, but that's not a little beyond the scope of what we're going to be talking about in this class. So if you do that, what you'll find is, and I'm just going to use hydrogen in this example because the hydrogen is the most abundant thing in the universe. What you'll do is you'll end up getting a spectrum that looks similar to this. I got green, and I got blue, and then I got purple, which is a permanent thing that I have to wash with water. But so what you end up doing is this is a chemical signature of hydrogen. So when you actually separate those light into through a prism onto, say, some screen, what you end up getting is the intensity bands of violet, of blue, of green, and of red that are characteristic of the energy levels of the atom. So each element has different characteristics, and we'll study some of those later on. So this is called an emission spectra. So let me just call this an emission spectra. And I'm going to get into two of the more complicated ones. So this is an emission spectra. Now this is for a very, very non-dense gas. If you just had some hydrogen floating around, this is what you would see. But when you have dense objects, what you have is many types of atoms in many different temperatures, so they have different energy states. They're all packed together. They're all different isotopes, and what ends up happening is it ends up giving more of a continuous spectra because throughout, if you add up all those things, they're all emitting from different atoms, from different energy levels, and they end up producing a continuous spectra. So a continuous spectra, I'm going to show a photo right here. This is the complete band of the visible spectrum that you will see from a dense object that is heated. So what that basically represents is, let's say I have a light bulb. It's a poorly drawn light bulb. Let's try it again. Let's say I have a light bulb, and I have a really dense filament up here. So this is the filament, and it's really dense. Okay. This I shine through a prism again, and that splits into the colors as I drew before, and then you get the continuous spectrum. So that's from a really dense object. So that would be what we call a continuous spectrum, which isn't really that interesting because it doesn't give us a whole lot of information, because this is all coming out white light, separating into all the other colors, as was shown in the picture. So what I want to talk about, what's really important in astronomy, is the spectra of stars. Because what happens is a little bit different with stars, and we get the reverse of the emission spectra. So let's say I have a gas here, a cold gas, and let's get rid of our little prism here. I have a cold gas here, and I've got starlight. Really, this would be like on the surface of a star, but we'll ignore that. This cold gas would be like on the surface of the star because the interior gas is hotter on the star. But as it passes through there, what happens is, as in the case before, where it allowed a lot of the light to pass through and absorbed only some of it and then would re-emit it, it's sort of what happens is sort of the opposite of that. Well, not really, but it'll pass all that light through. So if it passes a bunch of cold gas,
and I'm an observer over here. This is my eyeball, and it's passing through the cold gas here. A lot of the light will pass through, while what it absorbed from the elements within that gas cloud will not show at all. So here is a picture of an absorption spectra. Sorry for mispronouncing that, but an absorption spectra gives us an idea what the stars are made out of. The characteristic bands that are missing are actually characteristic of the element that is on the surface of that star. So that gives us a really good indication of what the composition of the star is. Most stars are helium and hydrogen, and this relates to temperature, which we'll talk about in a minute. But for now, I just wanted to define those three different types of spectra so we can talk about these next couple of topics. The Doppler effect is a property of sound waves that we're all familiar with, but it also happens with light waves, although not necessarily such a clear-cut matter. But the same thing exists, and that is the wavelengths get shorter if an object is moving towards us, like an ambulance with a high-pitched squeal, and longer as it moves away from us, like the ambulance after it passes us gets a lot lower in pitch. So this is kind of the same property as that we'll see in the spectral lines of a star. As we'll see them, if they're moving towards us, we'll actually see the compression of the wave, and as they move away from us, we'll actually see them expand. So, for example here, if I take a star and it's shining a green wavelength at me, and I'm the observer here. Okay, if this star is not moving relative to me, if it's moving up and down, I don't see any shift. Okay, but if it's moving toward or away, that's when the interesting thing happens. So let's just say it's moving towards me. And now that light wave gets compressed, essentially. And I'm not going to talk about the mechanism because that's a little bit tricky. So I get a much shorter wavelength. See this wavelength? So let's go back to defining our wavelengths. So I have this lambda here. That's one wavelength. That's the green wavelength. And I have this shorter wavelength for blue light, because blue light has a shorter wavelength. So what we end up seeing is a blue shift in the spectra, which I'll show in more detail in a second. So if it's moving away from us now if this thing actually is moving away from us, what we actually see is a, let's try to draw this schematically. So now it's moving away from us. Let's just draw these different scenarios with these eyes here, okay? So here's the eyeball that sees that. All right, here's the eyeball that sees that. So it's moving away from us now, and that wavelength stretches out. So what we see is a red shifting. We see those lines, the Balmer lines, shifting towards the red end of the spectrum. So this is the three different cases. Here is if it's not moving, if it's just moving transversely to us, or not moving towards a wave, but just transversely, or we're not really moving relative to us at all, we'll see this as the true wavelength that it's emitting. If it's moving towards us, we get the wavelengths crunch, they get smaller, and we ended up seeing it blue shifted. If it's moving away from us, we end up seeing this elongation of these wavelengths, all the wavelengths across the entire spectrum, and then we end up seeing it red shifted. This is a key to sort of like one of the key elements of the Big Bang, is that when we look at all sorts of spectra from stars really far, the further away they are, the more red shifted they are, so it looks like they're moving faster than us. And it appears that to be the case. So what I'm going to show you here is a picture of the spectra for an unshifted spectrum for a star. Okay, so now I'm going to show the case where it is moving towards us, and you can see that the Balmer lines from the absorption spectra have shifted more towards the blue region, and that indicates that the object is moving towards us. Now if I show the situation where the star is moving away from us, then we start to see that the Balmer lines tend to shift towards the red end of the spectrum. So if you look at the unshifted versus the blue shifted, you'll see that it shifts towards the blue end of the spectrum. If you look at the unshifted versus the red shifted, you'll see it goes towards the red end of the spectrum. So in conclusion, what we have here is a situation where we can determine, or not a situation, a mechanism in which we can determine how the stars move relative to us, which is a really powerful tool.
And one more thing I want to talk about is if this star is rotating, if I'm looking straight at a star, so let's do this scheme for a second. If I'm looking straight at a star, like these, right, and this side's moving towards me, I'm going to see the blue shifting like I was talking about a second ago. So I'm going to see the light on this side, blue shifted. If I look at this, and I can see that it's red shifted. So the rate that that spectrum travels back and forth is how we can tell what the rotation rate of the star is, and the rotation rate is actually related to the age of the star. So there's people who actually try to figure out the ages of stars based on this property. So the Doppler shift is a very important aspect for how we study astronomy. It's also an important aspect for police radars, because that's actually how they determine how fast you go, because they send a signal, bounces off your car, and if it's compressed, they can tell you how fast you're going because it compresses when it comes back. And so we owe the Doppler effect, we owe getting speeding tickets and stuff like that to the Doppler effect, because it works the same with radar waves that the police use. So that is a brief summary of the Doppler effect. The mechanism is tricky, but it is a very powerful tool that we can use in astronomy.